Hello, everyone, and greetings from Stanford to Hangzhou. Uh, I was here in Dream Town in 2018, 2 years ago. And last year, I was in Westlake. Hangzhou is really a beautiful city, and I wish I was there for this meeting, but unfortunately, we are all unable to travel. Still, I'm very pleased to reach you through this medium. Today, I'm going to talk about the era of human-robot collaboration. And in this slide, you can see how human is able to paint through a haptic device. And the haptic device is allowing the human to feel the brush, to feel the contact in ways that are almost magical. Robotics is growing, and there is a lot of excitement in the world, and there are a lot of expectations from robotics. Robots are leaving the factory floor, reaching closer to human, and we see that in medical robotics. In medical robotics, we are performing thousands and thousands of surgeries every day around the world. We are seeing major transformation of robots going to the factory floor, going to applications in domains that were very difficult to reach, such as agriculture, in field robotics, underwater, in the mine, in the factories, warehouses, in hospitals. In all these areas, we are seeing robots becoming part of the environment where human and machines are working together. A lot of progress has been made in mobility, and we see robots on land, in the air, underwater. We are making also some progress in manipulation, much harder. Manipulation requires physical interaction with the real world, and there are many challenges to do this properly. The challenge is the fact that when we interact with physically with the real environment, and when this environment is unstructured, the challenge is that manipulation requires a lot of careful planning. So the progress we have seen in manufacturing was the result of the fact that we were able to place fixtures, we were able to structure the environment so that we can pre-program the robot. The robot is playing back and back, again and again, the same task. Well, in the real world, the environment is not structured. And here you have an example of how a different modality of control allows us to perform the task. In here, we are relying on contact, and the contact is guiding the motion. The robot is rotating and moving in the right direction from the reaction forces it's feeling. And this is key to bringing robotics to unstructured environment. So there is a very major difference between structured environment robotics and the unstructured environment. Programming in structured environment relies on offline trajectories, whereas in unstructured environment, we need to create modalities like those used by human, which relies on touch and compliance. We need to be able to program the robot at much higher level using those capabilities. Offline trajectories rely on precision, and that leads to heavy and rigid robots, dangerous robots. Now we need safe and compliant robots. And that is a very different modality that is needed for unstructured environment. So in here, you have an example of how a robot is moving over a surface that is not stationary. And the robot is adapting to the changes in real time without having to change its trajectories because it's relying on the contact information. So humans make use of compliance, and a little child is able to open a bottle of milk, or a human is able to mold and maybe make prepare food without even thinking about it. And this is because we have skills, and those skills are displayed in real time. The idea that we have been pursuing is how we can capture those skills, how we can segment the demonstration of a task, learn from it, encode it in a robotic strategy, and perform it by the robot. Here is an example of how this is done, and you can see how the robot is learning a strategy and then able to perform the strategy for different geometry, different positions, and different orientations in ways that it would be very difficult to pre-teach. So the robot is acquiring a skill, and this skill is going to be taken to the applications in different environments. This is a perception skill that make use of touch and tactile perception to allow the robot to grasp a glass that cannot be visible. However, the glass now is grasped firmly without breaking the glass. So working with human requires also understanding human motion. We need to model human in order to interact with human. And this is something that we are doing, and we are doing because we are able to model human using algorithms from robotics. And now we are able even to model the upper body of the human with more precision and much more muscle representation that are obtained from scanning using MRI on specific subjects. And this is very important in order to interact with specific people. So the collaboration between robots and human is going to increase as we build those capabilities and we bring those compliant and safe robots. And that is going to be a transformative changes to the way we interact with machines and we build in manufacturing. Interaction with robots can take place in different ways. Physical direct interaction, as we see here. So the robot is guided by the human, and the robot is complying with the forces applied to it. The robot is safely interacting with humans, and it's moving away. It's not fighting the forces of touch. Wherever we touch the robot immediately responds and moves in the direction of contact. Another modality is through haptics. With haptics, we are able to create interaction where the human is guiding the motion and the human is feeling that contact. This is a very important modality, especially if we want to interact with remote robots. So remote robots can be so powerful in areas where we do not want to deploy human. Rather, we can have the worker placed in a safe location, interacting with a robot, and where the robot is substituting for the human. This is an example of the same task performed by the human, and the human motion is guiding the robot, and the robot is going to be able to disconnect this cable remotely, so the human and the robot do not need to be in the same space. This ability can be applied today to the current situation where we do not want to risk physical interaction between doctors and patient in the ICU room. And it would be wonderful to have robots that are assisting in this task. Of course, these robots are not going to be completely autonomous. We are going to connect these robots haptically, and the physician will be able to interact gently with the human, and the physician is going to be able to interact with other physicians and experts and acquire the data all remotely from the safe location of the office of the physician. So this idea can be explored by taking the robot from one room to another, where robots are disinfected in a special location and operated remotely from different locations. So we can see how robotics is going to affect the health, the medical field, wellness, the service, the industry, and many applications in field robotics. I'm going to show you an example of field robotics that we have taken at Stanford. This is a robot called Ocean One we built at Stanford, and this robot went to an expedition in the Mediterranean. This robot was built at Stanford, and here you can see the students assembling the robot. Well, this robot cannot be deployed in and operated or tested in the lab because it's designed to float in the water, and the only way to test it is to take it to the field or to take it to a swimming pool. So we're going to take it to the swimming pool, and in the swimming pool, the robot is going to go through a special ramp that would allow the robot to float. And once the robot is in the water, then the robot is going to have no weight anymore. The weight will disappear with buoyancy, and the robot here is being tested and controlled haptically. So haptically, we are able to interact with the robot, and you can see here how the robot is moving in the water and ready for its expedition. The expedition took the robot to the Mediterranean, and it was carried by a vessel called the André Malraux, which is a vessel of the Ministry of Culture in France. And the mission, this was an archaeological mission, taking the robot to 100 meters, where we have this vessel, and you can see on the right one part of the vessel cannon still standing. And our colleague wanted us to go and reach that area. You can see how we are controlling the robot haptically by interacting with the haptic device, monitoring the cameras seen in this control room. Once we reach and place the object that we recover in the container, we need to close the container, and then the containers come on its own to the surface, as you can see here. And then the container that came back to the surface brought a very unique object. This is an object that comes from 4 centuries, a vase from Catalonia, and this vase dates from 1664. And you can read the history of the sea on the vase, and this was a very exciting recovery of an object that was sitting in the water for so many years. Santorini in Greece for a mission on a volcano. The robot, after the first mission, was placed in the museum of the sea in Marseille in France, and many people wanted to come and see and visit with the robot. So we left the robot for a month before returning to Stanford. The media, all the media was there to cover that story. Now, this was also an incredible experience for our student, being together with scientists from archaeology, with marine biologists, with different groups, all working together. Over the past few years, we've been developing a new version of the robot, much more powerful, that is capable of going to 1,000 meters. And we just finished this last week, And in fact, I have a photo for you. Today I was in the pool with the robot, and here is the robot being controlled in the pool, and the robot is getting ready for another mission that will take us to 1,000 meters. Thank you very much for your attention.